And welcome back. In this series of slides, we're going to take a look at what we understood the memory hierarchy to be, which before was just, I got registers in memory. Are there more elements that we were hiding from you? And it turns out we were. So we're going to reveal some of the layers of the onion to you in this set of lectures. So again, let's go back to our library analogy. I'm writing a report using the library books. I'm going to the stacks. It's some English class. I'm freshman. And I've got to report the works of J.D. Salinger. So I could go to the library. What I probably do, by the way, is I go to the library, I look up the books, I fetch all of the books from the stacks. I have a stack, everybody sees the picture of people walking back after they collect all the books they're supposed to get. And then I'll find a desk in the library near enough that if I need to go back, it's not too far. And then what I'll do is I'll open all the books and I'll have them all open on my table and I'll be able to reference this book. And you've probably seen this. You've probably seen your classmates have that, where you have the books all around the table and you're kind of, you're writing a report on J.D. Salinger. Yep. I remember writing that last year. Yep. Thanks so much. That kind of thing. You're having no conversations with your friends. Now, if you need more, you go check them out. Now, you check them out until your desk kind of gets full. And maybe they say, sorry, you can't stack the books or something. So maybe there's a limit. So then you have to put some of those books back and you have kind of a working set. In a way, like you have a working set of books that are all laid out there. If they don't let you, because of damage to the books, that means you can't stack the books up. So you have a certain fixed limit, a certain size on your desk, but you're able to really save a lot of time. Imagine if I were to make much smaller desks, how much more painful that would be for you to only have one or two books and I have to keep running back and forth to the stack. So actually, we like the idea of having a really large desk. I can open more of these things. I actually like the idea that they can let me stack them, but let's say I couldn't do that. So this idea, this analogy of maybe that the 10 books that I have on the desk are enough to cover most of what I need. In the rare case I need an 11th or 12th book, I'll be able to do that. But for the most part, my working set of books that I have, working set of data that I have, is able to be very, very efficient. And the time to reach it is, boop, got it. That's how fast it took me to grab something. Rather than get up, go look it up again, go find it, walk the stacks, come back, get it, and bring it back and do the same. That would be painful. So this distance, the time, ready? 1, 2, 3, blah, blah, grabbing it. And that was about a second to grab the book and open it up. That was great. We like that. We like the idea of having stuff that we're going to use often close to us. And that's a great analogy, close to us. And I say close to us physically, but close to us in time as well. It's great stuff. That's the idea. Memory caching is exactly the same idea. That desk is in a way a local, it's a very fast to access, but smaller, certainly not smaller than all the books in the library, smaller collection of the data that I'm going to be using. And so based on the idea that the CPU versus DRAM speed curve just got larger and larger, that was crazy. We don't want that. We're going to introduce the idea of a memory cache. And this is, by the way, a big idea in computer science. If you talk about computational thinking, and in fact, I'm on some national committees to talk about computational thinking, and my perspective of what computational thinking is, it's thinking like a computer scientist. It's thinking of the world in a lens, in the glasses that computer scientists all walk around with all the time. And caching is one of those big ideas. I have it on my phone. You have a favorites list. You have a recently called list. Favorites is where you get to specify what's in your faster access. But the recently called list, if it only shows 10, that is, in a way, recently called. It's exactly the idea of what we're talking about here. It's like the recently used books that I had. So typically, the way we implement, we're going to build these caches, are going to be done with the same IC technology, the same processing technology as the CPUs, and even sometimes on the same chip. That's great. Same chip, really fast. Even physically, the farther you go from the CPU, from the registers, the farther you go physically in distance, the slower it's going to be to get there. Probably the bigger you're going to have, but the slower it's going to be to get there. I got my hard drive with a long cable across the room. I got a network of computers in the cloud, all those things farther away, larger, but really small and fast. So you want to have the caches be on chip if you can. If you can do that, you get great speed. The important idea, boy, we put it in yellow here, and I can't emphasize it enough. A cache, and this is, by the way, where the library analogy falls down. I grabbed the single copy of the book, and now it's on my table. It wasn't there, but in digital versions, it's not like one version of those bits. So the cache is always a copy, a subset of what memory had. Memory has, in a way, the reference copy, the reference values, and the cache is always a copy. is always a copy. In fact, for the first couple of lectures, we're going to talk about cache reads, where I'm only reading values. Only when you have storage do you have conversations of keeping the copy consistent. So for now, just think they're always consistent until I tell you otherwise, and I'm only ever reading from a cache, just to for now, let's make it easy, okay? Important. So say this to yourself. Cache is a subset, and it's a copy of what was in memory. That's the important idea. And by the way, this is also something we're going to see when I show you pictures of a CPU later. Most processors actually separate caches for instructions and data. You remember, in the place where code lived, instructions were down here and data was up here, right? You know, whether the data is static, you know, growing up from the heap or growing down from the stack, that's still a different place than the instructions. So rather than kind of corrupt them and put them all in one place, it actually makes a little bit more sense to have separate caches for only instructions, which are all the stuff down here, and the data, which all could be a large group of, you know, data could come from a large range of memory addresses, where the instructions probably come from a smaller, but separating them actually keeps it more clean. It's kind of interesting. So think about having two caches at least, an instruction and a data cache. Pretty cool. This is the picture. This is the picture of memory hierarchy that you've seen up till now. You got a CPU, the core is there. The fastest, smallest, fastest, and most expensive storage there are registers. They're amazingly fast, blisteringly speeds, but they're really small, not that many of them, and they're really close to the CPU, so I can get to them in easily one clock cycle. Fractions usually of a clock cycle. Farther away and down in this triangle is physical memory. The DRAM chip, when you say, I want to upgrade the memory, you're talking about that. The DRAM is the dynamic RAM, and dynamic means you have to refresh it. Dynamic means you have to kind of actually keep pinging it to kind of, hey, remember that it was a 1, remember it was a 0. You got to keep refreshing it. So that's why it's called dynamic RAM versus static RAM, but you don't have to do that. And reasonably fast, but priced more reasonably than, boy, every bit for registers costs a lot. Those are farther away. You know, I go to Fry's Electronics, if that still exists anymore, and I buy some DIMMs and I plug them in. Dual input memory module. So you could have a larger space. Because they're external, I can now swap them in and out, which is great. That's nice. Sometimes they burn on the board and you can't move them, but most of the time you can, most desktop computers, you can swap them in and out and increase. By the way, if you want to make your computer run faster, you're going to learn this when you learn about VM, virtual memory. Buy more memory. So talking about swapping it in and out. But ready for this? Revealing the layer of the onion. The layer of the onion! We're going to put caches in the middle. And they're typically going to be a different process. They're not going to be, sometimes they're going to be on the CPU, which is great, on the same core, on the same chip as the CPU. They are, as they're shown in this triangle, it's a beautiful triangle, it's consistent. And by the way, if ever you come with a technology that is kind of out of place, the market will sort it out. Meaning, well, what if I had this, if this could be bigger than memory? What if this could actually be bigger than memory without slowing it down? Well, then it would move down there and memory would be above it. Like it actually will, the market will move things around to automate that. It's really interesting. So it is, of the three parameters of this, it is faster than memory, but slower than registers. It is cheaper, it is more expensive than memory, but less expensive than registers, same thing. And it's larger. It's smaller, remember the triangle, it's smaller than memory, but larger than the registers above it. So those three parameters, it fits right in the middle of all the three parameters. Jim Gray was a Berkeley alumnus, got his bachelor's and PhD at Berkeley. He came up with this beautiful analogy thinking about if you had a fact or a piece of paper with like a secret thing on it, like a password or something, you need to get it, how long would it take? And making an analogy so people could, again, that was the library analogy. Now, what if you actually had the same idea, but in terms of relative speed to how long it would take to get to something? So registers, the model that you've seen before is registers, I can get to, as fast as I can, about a minute. If you say register is a minute, even though it's like 1 nanosecond, one clock cycle for 1 gigahertz clock is 1 nanosecond. So imagine if the analogy in a physical piece of paper is about a minute to get something. I'm thinking, oh, what was that number again? Okay, I got it. Okay, that's about a minute. Now, memory, the equivalent time for how long it would take you to get something from memory, we're going to talk about something in the hundreds to maybe even 1,000 times that speed. Usually it's several hundreds times that. So what's several hundred minutes? Well, we're talking about a trip to Sacramento. So that means you left a piece of paper, how annoying would that be, in Sacramento, and you gotta go grab that. That would be just terrible. And that maybe it's a book you're talking about, maybe it's a piece of paper with a password on it. Caches are like in the middle, right? In the middle of that triangle in the memory hierarchy. So the analogy there is, it's like it's in this room somewhere. Oh, it's in the room. Okay, I'll find it. Did I leave it under that? No, it's not under that. Under the plate? No, it's under. But searching the room isn't too bad. It's about 2 minutes. So we love caches. They are bigger than registers. Remember, registers, only a few of them. Now they're bigger than registers, but they're about the same speed as registers. You know, they're not that far away in terms of distance, at least the closest cache. We're gonna learn there's more than one cache, but for now, that's pretty cool to be able to have something that's much larger than registers, but just about as fast as them. A little slower, but not that bad. Maybe 1 or 2 clock cycles. That's great. So we love this. We love this analogy, and we're gonna actually see there are things way above Sacramento as we try to go to disk. How far is disk away? You're gonna see, be surprised how far disk is away in this analogy, in terms of how long it takes for, how many clock cycles would it take to go to disk. So again, I think I mentioned this before in my other memory hierarchy, but as we look at this triangle, here are some of the parameters about this. I think I might have said this. As you get farther away from the processor, you end up having increased access time, okay? So you're gonna be slower. It's just slower to go farther away from the CPU, okay? And what I mean is, it's not just like, it's the same speed, but farther, kind of like in the library analogy, just farther distance. No, you're going to different technologies, so it actually kind of, it's like walking through quicksand, and then walking through quicksand with a big weight behind you, and then walking through, so it gets slower and slower. The farther you go, you get to different processes, and you end up having different speeds as you get there. And that's just the same speed, but farther. Also, the relative size of memory at each level gets larger. So as I move away from the processor, I get bigger and bigger. So I have caches is smaller than memory, and we talk memory and secondary memory here. But so cache memory, secondary memory, which might be disks. So secondary memory we often call disks, which might be flash-based or might be of spinning cylinders. However we decide, that's what we call secondary memory. And if we include that in this conversation, the farther you get away from the CPU, it's still consistent. It is slower access time, larger, but we didn't mention here, it's cheaper. Another factor here, it's much cheaper the farther you go away. So the price for a single bit on disk, man, nothing. Price for a single bit in memory, still pretty good. Price for a single bit in cache, woo. Price for a single bit on the register, boy, that's pretty expensive. So, I mean, even in today's dollars, that's pretty expensive, thinking about what a single bit costs relative to a single bit on a disk drive. Interesting, okay? The other important thing is always, it's the inclusivity. It's always a subset. The smaller is always a copy of the larger. And every single one of them, every single layer from the processor working on something right now, it's computing something right now, to the registers, which is more set. But if actually processors, I had some data that's flowing on the data path, I'm working on 2 numbers. Okay, that's really, okay, smaller, and a copy of what was in the registers, a copy of what's in my cache, copy of what's in memory, and a copy in some sense of what's in disk. Remember what the loader does? The loader grabs, remember that? It grabs from disk and loads into memory. Memory's then a copy of what was on disk. Same idea. Pretty cool, right? Okay. So the trick, here's the whole beauty. This is a little longer of a video, but this is the beauty of this idea. The beauty is this abstraction. Abstraction is the key idea in this whole course. It's the abstraction that you're living at, forget the cost for a moment, okay? But you're living at the speed of the smaller guy, but at the size of the bigger guy. That's it. That's the big idea. It's like having, imagine like having, I don't know, the disk available to you at the speed of registers. That's the idea. And the idea of caches is, what if you had all of main memory, which was big, but at the speed of a process, in some sense the registers, but you know, something faster than that. The speed of, it's really the speed of the cache, but what if you had access to all the memory at the speed of the cache? It's not registers, but it's pretty close. That's the idea. So this whole beautiful idea, and look at the numbers here. So the speed in cycles, I think I want to circle some of these things. So, you know, how fast is it to get to the reg file? You know, half of a clock cycle. Well, how about to get to the, you know, the caches? About ones, you know, in the single digits of clock cycles to get to the cache. Well, how about main memory? You know, we talked about this, you know, about 1,000-ish. That's Sacramento. How about disk? Boy, you don't even want to know how far away disk is, okay? And this is the size, the highest is the highest cost in the small guy and the lowest cost here. And the size is roughly like that. And you turn me out, well, how big do you mean this triangle? Well, what's the width of that triangle? I've in the order of hundreds, they had 32 registers, something small. In the order of like 10,000-ish for caches. Memory, you know what size memory is. Memory is in the GB, usually several GB, and disk is typically in the TB. So it's interesting to see what the width is typically for computers and technology today. And that number is changing every year. So those are the on-chip components. The things that are on chip are the cache. That's the idea. So some part of the cache is on chip, and that's just great. So summary of the whole idea, if the level is close to the processor, the higher up you get in that triangle, the memory hierarchy, it is smaller, faster, and more expensive per bit. That's clear. And also the important thing is a subset of the lower levels. I think I said that 4 times now. I want to make sure that you don't get that question wrong on the exam. It's always a subset, a copy of the lower levels. And the idea of the memory hierarchy is the illusion. It's the illusion. Woody Allen has a line that says, I put some backlights, by the way, I have backlights here in my studio. I put some backlights behind me to give me the illusion of 3 dimensions. So same idea. The idea here is in this hierarchy, I have the illusion of the size of the lower levels at the speed of the upper levels. That's it. That's it. That's the big idea. We'll talk about how to actually make this work the next lectures. We'll see you there.